Hi, this is Ken Johnson for another episode of SecCast. This tutorial is part of our Ruby on Rails secure coding series centered around OWASP's top 10 list. Today's tutorial will cover sensitive data exposure and how it can occur in Rails applications. What is sensitive data exposure really? Well, it used to be that OWASP had a category that dealt specifically with insecure cryptographic implementations. My guess, and this is purely a guess, is that someone determined that focusing solely on the cryptographic mechanisms as a way of leaking potentially sensitive data in unintended ways, well, it just wasn't sufficient. After all, you must consider what your application logs, what it sends, how headers are configured to avoid caching, sensitive parameters sent in GET requests, and much more. Together, we will cover some of the basics as it pertains to this category and demonstrate how these flaws are created as well as how they can be fixed. Let's get started. The following scenario is more common than it should be. We have a page that returns the last four of a social security number. During an initial glance, it would appear that only the last four of a user's social security number is returned. When we inspect the element, all appears as it should. We then view the generated source. This is the state of the source code after all JavaScript events and triggers have executed. And once again, everything appears normal. Next, we view the raw source. Here, we see a big problem. The social security number is actually returned in full from the application. Code on this page later obfuscates this value. Navigating down into the source code, we see the JavaScript function that performs this obfuscation once the DOM is loaded. In essence, it replaces the first 5 digits on the page with asterisks. Why is this bad? Isn't this why we have SSL? Yes and no. Yes, this sensitive communication is part of the reason we have SSL. Is this the only protection we want to rely on? Absolutely not. I'll offer up 2 points for this particular scenario, and remember, every scenario varies. From your browser to the web application server and every hop in between, requests and responses can be logged. It's an unnecessary risk. In this circumstance, it is clear that there is only a need for the last 4 digits and nothing further. When another vulnerability is introduced, it may be possible to see other people's data, and in this case, you want to limit what you provide. Our video on insecure direct object reference is a perfect example. The video shows an attacker changing their user ID in a RESTful parameter to another user's ID in order to view someone else's work information, ultimately allowing the attacker to capture another user's social security number. Okay, so hopefully I've convinced you that there are times where unnecessary risks are introduced when it comes to sensitive data. Let's focus on fixing the problem. We know that the full social security number is disclosed to the user, but given that we've received plain text data, it is possible that this information is also stored in the database unencrypted. If this is the case, it is a serious problem that needs to be fixed. We can see through a review of the database contents, the social security number is stored unencrypted. This is another issue. We'll solve both problems. If you have a copy of RailsGoat, you can follow along here. The link to the RailsGoat repository is under the references section of this tutorial. Firstly, let's uncomment our work information code in the seeds file. This code both creates new work information but also instantiates a key used as the initialization vector during encryption, which is different on a per user basis. While we're at it, we'll comment out the legacy work information code. Next, we'll want to uncomment the encrypt SSN before save directive, and we'll want to change SSN to last 4 in the view. The last 4 method will strip out all but the last 4 digits of the user's social at the model layer. You can see that we have an encrypt SSN and decrypt SSN function available for your review. The important thing to realize is that we are encrypting and not hashing so that this value is reversible. We leverage unique per-user initialization vectors as well as a server-side key along with the social security number to perform an encryption and decryption routine. Note that the full SSN column is now empty and the encrypted SSN column is populated instead. Even if the attacker could access the database through SQL injection or through some other vulnerability, it would be a difficult task to decrypt these values without access to the server-side key. Note that we use the blob type to store this encrypted data. We'll try to review this page again. After accessing the source code, we can see that only the last 4 social security numbers are returned this time. So we've successfully fixed 2 issues by being a little bit more cautious with regards to how we both store and send sensitive information. In this section, we'll discuss the danger of using weak cryptography. In the next example, we show hashing passwords using MD5, which is basically terrible. I believe, or at least hope, most developers are using a more secure hashing algorithm than MD5. Still, we'll show the dangers of using such a weak cryptographic implementation. We'll sign up with a password of test. After having signed up, we want to navigate to our database and open up its contents. You can see that we have a column named password, which is storing 32-character MD5 hashes. Next, we'll copy and paste that MD5 hash into a website dedicated to cracking hashes. After entering the hash, CAPTCHA, and submitting our request, in just seconds the correct password is returned. This bit of video was not edited. The password hash was really cracked that quickly. Okay, so what does the vulnerable code look like? We have a before save call to hash password, which performs an MD5 hash of the password upon save. We now want to fix this issue and leverage a secure algorithm such as Bcrypt. To do this, we need to comment out the old authenticate method that gets called during, you guessed it, authentication. And we will change this method around so the comparison is between 2 Bcrypt hashes versus 2 MD5 hashes. As you can probably guess already, we are going to need to remove the password column from the database and add both a password hash and password salt column. Next, we need to build the hash password function so that we both generate and save a salt on a per user basis, which adds to the entropy of the hash as well as generate a password hash leveraging the password provided by the user in addition to the salt. That final hash will be saved in the database column named password hash. We'll generate a migration that will add our password salt and password hash columns to the database. Then we'll generate a migration where the password column is removed. Finally, we'll perform the migration operation. We also need to add an attr accessor of passwords so that our existing code does not have to change. A password attribute will still be assigned a value, and upon before save being completed, that password field will be turned into a password hash, with the salt having been saved on a per user basis. Lastly, we need to drop and set up the database as well as restart the server for our changes to take effect. We'll go ahead and sign up with the same information, including password, as before. We'll navigate back to the database. As you can see, we store our hash, which contains both the salt and password hash, part of Bcrypt standard, and our salt column used during the authenticate method. So we've converted our weak hashing mechanism into a new password hashing mechanism. Obviously, in production, users will need to have their passwords converted over before leveraging the new mechanism. Usually, this consists of validating the old password hash against the password provided by the user during authentication, then converting the password to a stronger hashing algorithm and marking an entry in the user row that indicates the conversion has occurred. Again, the overhead isn't really so difficult that it should deter developers from continuing to use weak algorithms. If your data is stolen, you're going to thank past you for taking time to protect future you. Model attribute exposure is a fairly simple concept. RESTful APIs and Rails often provide details about some model object in a JSON format. You can leverage as JSON to convert an entire model object to JSON and pass it back to whatever client made the call. The important thing to remember about this is that all model attributes are returned. This may not be ideal and unnecessary. For example, we have code that returns a user object and we call .asJSON. Unfortunately, all of our information is returned, including sensitive information such as our auth token, which we really do not want others to have. We'll navigate to our user model, uncomment our asJSON method, which overrides the original implementation and says only these attributes are allowed to be returned. Once we re-request our information from the API, you can see that only the 4 attributes we specified as being allowed are returned. I've heard of other folks using Rails serializers to provide the same sort of functionality and protection. This seems like another viable way to sanity check the information that is returned to a user. Logging of sensitive information is actually somewhat straightforward. Here, we've added a link where a user's social security number is passed as a parameter in a GET request. You can see this as we've posted the link in our browser for clarity's sake. Okay, so when we click on this link, the request parameters as well as the request path are automatically logged by Rails. Clearly, we don't want social security numbers or any other sensitive data for that matter being stored in our logs. To fix this, we can filter out certain parameters from within Rails. Now, to be clear, this will not work if you call something like rails.logger.info, for example, and pass it the params hash. To Rails logger, it is just an active support hash with indifferent access object, and it will not attempt to perform filtering in this scenario. Instead, the filtering of parameters pertains more to the automatic logging that Rails performs. Okay, so we've added the SSN parameter to our array of parameters that must be filtered when Rails performs its automatic logging. Next, we restart our web server so that our changes take effect, and navigate back to the web application and terminal where we are viewing the development log in real time. We re-request the same link, and this time you'll notice that the SSN parameter is filtered both in the path portion of the request as well as within the parameters listing. While we are on the subject of passing sensitive parameters in a GET request, let's quickly address why this is an issue. Beyond server-side logging, it's important to take into consideration all the points at which HTTP data is stored in its journey between a client and web server. Additionally, users' browsers cache this information, and if a user's browser is compromised, you want to help them protect themselves as best as possible. To demonstrate what I mean, here we navigate to the cache section of our Firefox browser. You can see our request is cached and sensitive parameters stored. This is far from ideal, and again, the user's browser is not the only place this request path will be logged, so keep those sensitive parameters in the body of post requests. To recap, we've discussed how no cryptography, weak cryptography, and logging can lead to the unnecessary disclosure of sensitive information by an application. I'm Ken Johnson. This has been another episode of SecCast. Thanks for watching.